Well, hello. Welcome to Exploring Creation with Physical Science 3rd edition, Module 6, the Study Guide edition. All right, I've got in front of me here a photocopy of the study guide so we can write in it together. And let's start off with some terms. Reference point is, look for the key words when you're taking a test. If it says point in the answer, then that's probably a hint that says it's a point, there's a point, against which direction is measured. Displacement, as we remember, displacement is always that position from the starting point that it ends up in. And so you got to have the word starting point in it, and there we go. So it's going to be the distance an object travels plus the direction from the starting point. Okay? Vector quantity. Vector quantity is always going to have a number and a direction in it. So that's what we're looking for in the answer for vector quantity. It's number and directional information, like 35 miles per hour northeast. It's got to have both. Scalar quantity is going to be just the number without the directional information. So here it is, does not. A key to taking tests is to read the fine print and watch out for those little tiny words that change the whole meaning of what you're doing. So scalar quantity is no directional information at all, only a number. Average speed. This one is a trick one because in the student study guide, there is no option for average speed, but it is in the answer key and in the textbook. So there you go. It is the ratio of the total distance traveled to the total time of the trip. So just think of like the mean, like you determine it in math. There you go. It's the total of something divided by the number of something. And so this is the time of the trip. Instantaneous speed is that moment in time that we want to get the speed for. Okay, so that is a rate at which an object is moving at a certain moment in time. So instantaneous speed goes whoop, right up there. Acceleration. Acceleration is the time rate of change. It's the process of elimination here. It's the only one left. That's one hint. There we can see a clue. But it's also the change word. That change word is critical when you see the word acceleration. We must connect acceleration with the word change in our minds if we want to remember which answer is going to go with acceleration. All right. So motion is described with respect to, because it is relative, motion is always relative, we'll have to pick a frame of reference. So that's your answer for that one. Two or more displacements can be combined by what method? So the answer here is using vector addition. Okay, so when we add vectors together, we get a vector quantity. So, or we can get the displacement total. All right, so B. What is acceleration equal to? This is the one I was looking for here. It is, we've got to really hone in on, is it multiplied or divided? And we know that acceleration is the change in speed, but is it divided by time or multiplied by time? Well, it's over a number, so it's divided by, okay, like my crazy circle there. If an object's position, hold still, does not change relative to a reference point, it is in motion relative. It doesn't actually ask this like a question. It is in motion to that reference point? It's almost incredulous. If an object's position does not change relative to a reference point, it is in motion relative to that reference point? Well, this one is a trick question. Says that the position did not change right here. So it didn't move. So trick question, no, it didn't move. Okay, sorry, paper's falling here. Say nope. So we're not falling for it. Apologia. We're not doing it. All right, so here we go. Number 6. Turn the page of my tricky answer key in front of me here. All right, so a child is floating on an inner tube still on a lake. His position does not change relative to a tree on the shore. He watches 2 girls jogging along the shore of the lake, and the girls are keeping perfect pace with each other. Neither is pulling ahead nor falling behind the other. Relative to whom is the child moving? That whom is actually a hint because the answer is probably not going to be a tree because the tree is not a who. So the child is in motion to the 2 girls because the 2 girls are whom's and they are moving, and the child is not. Even if he was moving, but not moving perfectly with them, he'd be moving. So relative to whom is the first girl in motion? Well, the only other person besides the other girl riding with her is that child. So it's going to be the boy. Okay? Because they say his. So we're going to say it's boy. And relative to whom is the second girl not in motion? Well, I think that's obviously the other girl because they're running together. Other girl, number 1. The girl number 1. Either answer there, it's fine. All right, moving on. Label each of the following quantities as speed, distance, velocity, acceleration, or none. And also identify each of these as a vector or scalar quantity. All right, so this one, I wanted to give you guys a clue because in the test, they ask a question just like this, but they don't give you all of these options. And so just watch out for that. They just say, identify these amounts and as what they are. And I forget what their term was that they used, but they don't give you options. So be aware and let's learn how to identify these different ones, okay? It's different quantities. So we have 10 meters. Wow, 10 meters is a distance, right? So we can call that distance. And they want to know, is it a vector or scalar quantity? Well, if there's not a direction on here, it is not vector, okay? So we're going to say this one is scalar. All right, 1.2 miles per second squared east. Well, that squared is a big hint. When we see that squared and we have all of the other things right here, we can say, whoop, ding, 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 ding. There has been change happening, acceleration. So we're going to go with acceleration. And because we have all of the things we need, we're going to call it a vector quantity. Okay, got to have the direction, got to have the amount with the miles per second. All right, now we've got the amount here. We've got the feet over hours, which means feet per hours, 3.4 feet per hours, but we do not have a direction here. So slowing is not a direction. If it had said up or down or north or south or anything, it would have been a direction. So we know already we're in a scalar, and beyond that, we can say that this is a speed because it is missing the direction, right? Feet per hour. So we've got speed going on. And I'm hesitating only just because you cannot count on this, answer key here. It said C is liters, is a volume unit. Well, that's D, and everything's all mixed matched here. So D is not going to match up at all. Is volume unit, so it is none of these options. And because there's no directional information, it is a scalar quantity. So we're going to say none and scalar. On the test, they won't have a none option because they didn't give you choices. So you'll always be using distance, acceleration, speed, or velocity. Okay, so let's look at this one. 2.2 miles per minute west. Well, when we've got a distance over time and a direction, we've got ourselves a velocity, and it's a vector quantity because we've got our direction. Okay, so velocity, and it's a vector. 2.2 millimeters per year. Well, that's about the same as this right here. We've got a distance over time and nothing else. And so that also has to be speed. Hope that made sense. Okay, and so which is speed is scalar, and there's no directional information. Okay, so scalar, no directional information, vector quantity, we have directional information plus the distance. And I don't think it has, I don't know if it has to be a distance over time or not. That's a really good question, Mrs. Wigton. We were going to have to research that. But it seems like all of these have a full-on distance over time or some sort of, there's more than just distance. All right, so I'm guessing vector could be just a measurement, though, with the direction. All right, number 8, let's move on. To find the speed, you must use equation 6.1, but make sure to check your, okay, so they want the speed of a boat that travels 10 miles in 30 minutes. Give your answers in miles per hour. Well, look at that. They give us minutes here, hours here. So what are we going to do? Well, we're going to look at the book. So their handwriting is super, super neat. All right. So make sure you can see it here. Always list your steps. When you're taking the test, be sure to do these really laborious little extra details, even though you can probably do the math in your head. And here's why. It says in the back that you get extra points for each step that you wrote out. So it's worth your time and energy to write out the distance, the time, and what you're looking for. And so we're just copying out what they gave us in the question. And excuse me, we've got 30 minutes. We're going to convert here into a half an hour. 0.5 of an hour is a half an hour. And so we got a decimal, and we've got it in hours. We already had, we just needed the hours to match. And so, because we're moving to miles per hour and out of the minutes. Okay, we're using velocity equals distance over time, plugging it in. And we've got 10 miles divided by 5.5 of an hour. Solving it out, and we have 20 miles per hour. This is a speed. It is a scalar. It has no directional information on it because that's not what they asked for. They asked for speed. Okay, so you're good to go right there. All right, number 9. I'm going to move things without making you car sick as best I can here. I am in the car. This is like the quietest place in my life. All right, so what is the speed of a jogger, number 9, who jogs 6 kilometers in 45 minutes? Please give your answer in meters per second. So we got kilometers there and meters. So we got to convert that. And again, I'm going to try to maneuver here without annoying anybody here. Here we go. So this is about the same deal. List what is needed. We've got the distance, the time, the velocity, conversions here. And to do that, if you're not sure, we've got, we just put that number over 1. If we need to match up a fraction, we just put the number over 1 and we get ourselves a fraction. We know there's 60 seconds in a minute, so we write that like that. And then because we can eliminate those minutes, because we've got it up top and down below on opposite sides of the multiplication sign, we now just go straight across over 1, and we just leave that off over here. And we've converted 45 minutes to seconds. And there it is. Or you can do it in your head, but you don't get as many points on the test. So write the equation out. Velocity equals distance over time. Same dealio here. And we plug it all in. There's our 6,000 meters over 2,700 seconds right there. And we solve it out, and it becomes 2.2 meters per second. I am being very trusting here of this book that has failed me a number of times. I should probably get my calculator out, but I'm actually recording on my calculator, so I can't really do that. Sorry. Okay, so let's move on. All right, so that was 9. Number 10. If a river current is 8 meters per second downstream, and a boat is traveling 10 meters per second upstream, what is the boat's speed relative to the riverbank? Okay, so one's going down. That's Maisie. I hear you back there sighing. Big dog sigh. So they're going opposite directions. So what do? Do we add them or subtract? Subtract them. Which one? Well, I'm asking you like I'm going to hear you through my phone here. But as I recall, we add them together when they're going the opposite directions, and when they're going the same direction, we subtract them. So for adding them together, we can do this pretty quickly in our head. That they're going to be 18 meters per second. But guess what? Guess what happened? The actual the answer key. Don't you love it when big authoritative things make boo-boos? Sure enough, there's an error here. It says that you would subtract them, but no. I'm not just going from memory. I looked it up. I double checked it on the internet. So there's a whole different source outside of this textbook, verified in the textbook. But sure enough, when they're going opposite directions, you add them. Everybody said so, except for this little error right here. So we're going to override this and write the word add in for the in the answer key. The boat's relative speed to the riverbank is, another thing you don't do here is you don't change the sign. So that's just a positive 8 plus a positive 10. You add them together and you got yourself 18 meters per second. They had the wrong answer there. Okay? So, all right. Oop, we saw the answer to the next one. No cheating. No cheating. All right, so we're on 11. If two displacement vectors add to give a total displacement of 0, what do you know about these two displacements? Well, what I remember from this one is you go this way too, and you go this way too. There's 0 displacement. We know that it went as far away as it came back, so it went in the opposite direction. So that's what we know about it, is that the amount that it went away and the amount it came back were the same amount, and we know that the directions were opposite. All right, a fly is walking on a wall. First it crawls 1 meter up, then 1 meter to the left, and then 1 meter down, shall we? So 1 meter up, left, and then down. And then they want to know its displacement. Well, we know this is 1 meter between, so it's 1 meter to the left. That way is left, right? So 1 meter to the left. That's the answer. It should be harder, huh? A car and a truck are traveling north on a highway. Nope, my book's in the way. Sorry. The truck has a speed of 45 miles per hour, and the car has a speed of 57 miles per hour. If the truck is ahead of the car, what is the relative velocity? So, this one, remember, when they are going the same direction, you want to subtract them from each other. And I always thought that it had to be the one in front minus the one behind, which in a way it does, actually. I don't talk about that, and I'm going to show you what's in the answer key about it. Step 1, list the information given to you. There it is. We just looked at that. Write it all out. We know it's subtraction. They got it right this time. Yay, book! And then there we go. Fill it in and solve it. Okay, well, they flip-flopped them around, but they said that, see here, they're coming towards each other. It's 12 miles per hour towards each other. So what's interesting about this is if you had kept it as 45 in the front, which was the car that was in the front, or the truck, sorry. The truck was in front, and then the car was behind. If you flip-flop this around, you would get a negative 12, and that would kind of be a way to show that he's gaining on it, and that's what it's saying. Why it's saying towards each other is because the truck is catching, or the car is catching up to the truck. So that's why the directional information here is, instead of they're both going the same way, it says they're going towards each other. I think it's because that ultimately it would have been negative if you had kept them the right direction. But it's important to note. Another way that you could have said the direction would be they're going. Would we switch it? Would we switch it? Okay, so it would be negative 12 miles per hour north, or 12 miles per hour south would be another way to do it, to flip-flop it around to say that there's one's gaining on the other. But we'll just stick with the book for this one because Mrs. Wigton is not a physicist. All right, so 12 miles per hour toward each other. I just like to think about it, and I'm learning too. All right, so I hope you didn't see the answer just now to the next one. That's cheating. No more cheating. All right, so here we go. If an object travels for 15 minutes with a constant velocity of 12 miles per hour west, what is the acceleration? So this is one of those trick questions. Is constant, it says so right there, it's constant velocity. There is no acceleration. So that's the answer to that. Number 15. The train takes that's 16. A sports car goes from a velocity of 0 to a velocity of 12 meters per second east in 2 seconds. What is the car's acceleration? So they write this one all out. Here we go. And write your unknowns. It starts out, it stopped. The final is 12 meters per second east. It took 2 seconds to get there. And we have our equation. We have our equation filled in with our final velocity first and our initial velocity last, over to the 2 seconds it took to get there. Solving the problem ends us up with this crazy 12 meters per second 2 seconds squared, or 2 seconds, sorry, not squared yet, over 1. So we don't want to say meters per second because that's crazy. And so we do this whole shebang. And so I wrote it out here, made a boo-boo up there. But so if we have that 12 over 1 second, we have the 1 over 2. I'm going to pause you for just a second. Okay, sorry about that. So what I forgot is that this is a division problem, and so in order to divide, we do that handy dandy thing where we don't ask why, just flip the last one and multiply. I can't remember the rhyme, it was so great. So we flipped that 2 over 1 or to the 1 over 2, go straight across. And we've got 12 over 2, which we can work out to be 6. And then we can keep our seconds per squared. Now we don't have to do the per second thing. And don't forget your eastbound. And that's what the original direction was. All right, number 16. All right, so looking at the question first. Here we go. A train takes a long time to stop. That's what makes trains. Maisie's sighing again. Oh, Maisie. That's what makes trains so dangerous to people who cross the tracks when one is near. If a train is traveling at 30 miles per hour south and takes 12 minutes to come to a stop, what is the train's acceleration? It's 'cause they take so long to stop. Okay, yes. So here's the initial velocity. This is the final velocity. It took 12 minutes to stop completely. That's a really long time. All right, we're going to do our conversions. So we have we have minutes and hours, and we can't have all that. We have to have everything in the same quantities. There's our formula. You're going to plug it all in, and it says continued on the next page, so hold tight. Here we go. Solving this problem. Here we go. And we work it all out, and we end up with 150 miles per hour squared. They do all that multiplication flippy floppy thing without you seeing it, but that's what I just showed you how they did. That's what they did right here again. All right, so number 17, describe a situation in which you can accelerate even though your speed doesn't change. They gave us a wonderful example of that in the book, and that was the carousel. And I cannot think of a better example than the carousel. So just you know that, why are we accelerating? Well, not because it just got started and it gets faster and faster for a while, or it has negative acceleration at the end when it slows down, but actually it's changing directions. And as you recall, that anytime anything changes directions, you have acceleration. Change, remember, that's the word that goes with acceleration. Change, change, change. Okay? Number 18, if an object is moving with constant velocity, what do you know about its acceleration? According to this, it says acceleration is the change in velocity divided by the total time. If there's no change in velocity, then the acceleration is 0. Okay? That's 18. Number 19, we're going to look at this graph for this. All right, they're asking, what was the person doing between 0 and 8 seconds? And then again, what were they doing between 8 and 16? So according to this, because we have a distance over time, that would be Ezra sitting beside me here in the car. He's done doing his violin lesson. He's going to wait patiently now. We've got, this is a speed graph, not an acceleration graph. So speed graph wise, we have constant speed, okay? Because it's not changing. It's just like continually moving the same amount of this amount of displacement, same amount of feet over the same amount of time, equal amounts of time. So we have constant speed here, and then because this is a speed graph, remember that's key, and then we have the person over time not making any progress in their footage, or the meterage, is that a word, that they're moving. So that means the person is standing still. If this was an acceleration graph, everything would be different here. This would not be the same answer. So beware of what kind of graph you're looking at. Usually acceleration says acceleration graph on it somewhere. Okay, last question. Whoa, how fast is the person walking during the first 8 seconds? Well, all we have to do for that is take our velocity equals distance over time equation, and we have how far did they go? 16 meters over 8 seconds, and we can do that math in our head, and that is, or we can look at the answer key right here and see that it is 2 meters per second, and that's all it asks. It asks for their average speed, and so that we don't have any directional information on that. Okay, so that is the long and the short of the study guide for this wonderful chapter in exploring creation with physical science. And I would show you Maisie, but it's so dark in this car right now. You're not going to be able to see her. I'm sorry this is so long, but I hope it helps you study for the test, and you're going to do a great job. And just by showing up and trying this, I just know you're going to do great. So take care and have a wonderful, wonderful rest of your day. Bye-bye.